Our next speaker is Professor Jie Wu from Beijing Institute of Mathematical Sciences and Applications. The talk title is Simplicial Topology, Braids, Nodes, and GLMY theory. Let's welcome.
Okay, so first of all, I would like to thank the organizers for giving me this opportunity to report my research. Right? And well, basically, you can think about my research could be considered as a higher categorization to approaches to topology and it's interdisciplinary research. So the part of this, I would say that are three parts in my talk today. So first part will be actually, as we say, use simplicial techniques to solve some core problems inside algebraic topology. That means a homotopy of numbers. And the second part of my research is using these simplicial theories to establish some fundamental connections between algebraic topology and say low-dimensional topology. And last part, I try to explain that you actually use this again use simplicial technology. We can make algebraic topology into applications and develop a new theory called GLMY theory. Okay, now let's move to the first part. So the important notion of this simplicial theory is called simplicial set, which you can think about is a generalization of simplicial complex introduced in 1950, which this notion of simplicial set, the purpose is to as a convenience category for solving problems in homotopy problems. Okay, so simplicial complex, you can solve the homology theory, is very good. But the simplicial set can be used to solve the homotopy problems. Now, I'll display the concrete definition of simplicial set. But if simplicial complex, the basic idea is try to introduce like this singular simplex. So, for example, you can think about this is say B0 to consider as a singular simplex means like V0 V0, right? So the length 0 of the edge. And keep going this procedure, then you introduce so-called degeneracy operations. And then you work out, as a sequence of a set and as a generalization of simplicial complex. Now, this setting is actually important. Okay, so one thing is nowadays people use a lot to do these categorizations. You can see that simplicial set is actually one-to-one corresponding to contravariant functions. So the category of finite ordered set. Okay, so you can see these monotone functions. And two, the category of sets. So once you realize this, of course, you can change the category of sets to the arbitrary category. So you get simplicial objects in any category, right? So for example, you can do simplicial groups, simplicial abelian groups, simplicial Lie algebras, whatever you can. Okay, so that certainly people you generalize this idea. So the domain, you can change the simplicial category to be, as I said, simple category like just a finite ordered set and the monotone functions, right? You can replace by any small category. So that's be a lot of study, and you can do homotopy theory on that as well. And also in this setting, the category of simplicial abelian groups actually is equivalent to category of abelian chain complexes. Okay. Well, these categorical ideas actually was developed a lot in history. Say in 1970s, Quillen has actually basically used these ideas, what he call homotopy algebra, okay, instead of homological algebra. That gives foundational works in algebraic K theory, right? You can introduce higher K groups. And well, Voivodski is actually also, he's an expert for simplicial homotopy theory and apply to algebraic geometry and algebraic K theory. Even he pushed further to give now like his mathematical logic, it's a homotopy type theory as well. And if you move to more recently, a lot of people working on this higher category. So Jacobo Rulli has introduced, say, according, just look at the definition. Okay, what does it mean infinite category? Well, one definition is like, this is a simple set satisfied weak conditions, which is actually the extension of the generalization of a nerve complex of categories. Okay? And you can see the infinite group means fiberless simple set. Okay, so now, let's back to look a little bit. So the question of the fundamental question, how to develop homotopy theory in the simplicial setting, right? All we can call in discrete world, we try to do all these homotopy theories. And this theory actually was well developed in 1950s, like by Dan Kahn, and actually a lot of beautiful work by John Moore as well. So I just highlight a few things, what we should do here. Now, one important concept is called complex, or in previous slide, you see infinite groups, right? Another way you can say this is just fibrant simple set. What does it mean? Just a simple set goes to the constant one, like one point space model, it is a fibration. Of course, you can, Dan Kahn was displayed that you need to satisfy certain extension condition. And Dan Kahn also constructed that for any simple set, you can produce a vibrant one, what he called EX infinity. Now, this kind of construction, if you're familiar with some elementary algebra topology, you know, for simplicial complex maps, any continuous maps between polyhedrons, you can, in the domain, you can do subdivision, barycentric subdivision, right? If you do sufficient times, actually you get simplicial map approaching to any continuous map. Now the extension here, you can think about the dual of the subdivision function. Okay, so now another thing I would say that there's an important thing in homotopy theory is so-called fibrations. And in simplicial setting, there's corresponding fibered map. Okay, that's geometric realization is actually second fibration, which was proved by Quillen, I think, in publishing Anderson in 1950s or 60s. Okay, now another one important theme in geometry is about fiber bundles, right? And it turns out that there's a corresponding setting called simplicial fiber bundles. Well, it performs perfectly as what you do in geometric way. Now, there's one interesting part of this simplicial fiber bundle. You can introduce the notion of a twisted Cartesian product to do that. And this is given by, geometrically, think about fiber bundle. And you can look at the chain levels. If you look at the chain levels, you try to deal with homology. That exactly goes to the Brown's twisted tensor product. This work was done in 1959. If you look at the history of this one, it definitely highly impact. Being Brown's twisted tensor product used the cap product. So Witten was produced the twisted the Hahn cohomologies usually take these ideas. Okay, so here I just say a few things on simplicial homotopy theory. Okay, so now one important thing in homotopy theory, you have to how to deal with homotopy groups, right? And as we say, just switch the category of the set to groups. So this is so-called simplicial groups theory. And there's a there's a lot of beautiful work in this direction. Well, essentially we can say geometric realization of simplicial group is a topological group. Exactly what we need. In Milner's work, he needs some conditions, say, completely many elements or locally finite for that. But if you retreated the topology, like compact general topology, actually you can easily to see the category of a geometric realization of simplicial group. It is a topological group. And the category of simplicial group is actually equivalent to the homotopy category of the loop spaces. Okay, so that's the, and now also you nothing to be worried about this so-called the Kamp's extension property for simplicial group, which automatically satisfy these Kamp's conditions. What does it mean? It means that you can homotopy theory directly using this simplicial group without considering the geometric part. So, okay, so that's like the, if you, right? So the Kamp's condition is an important thing that you can look at the homotopy simplicial maps and look at the homotopy of simplicial maps in setting in a fully in simplicial way. And that's exactly the same as homotopy classes of the continued maps between the polyhedrons. Okay, so that's why you can convert the geometry to the simplicial. And now the another interesting thing is that you may wonder to know whether you can produce the homotopy group as what we produce for homology group. In other words, whether you can construct a chain complex whose homology just given by a homotopy group. If you use the notion of simplicial group, it will work. And this was done in 1950 by John Morse theorem. So you, for any simplicial group, you can produce so-called more chain complex. That is actually, you use these faces, now become to group homomorphism, right? So you take the kernels of the faces, just accept the D0, okay? Except the first one. You take the intersections and the filling back D0, that gives a chain complex. And whose homology is exactly homotopy group. Here, homotopy group means the homotopy group, you take a geometric realization of the simple group. So in terms of theoretically, it at least looks like beautiful. Now, the one more common is that, well, for giving a simple group, what can you do? You can look at the filtrations by subgroups, right? Simple subgroup. And that exactly you will produce a lot of spec sequence on homotopy groups, right? So for unstable atom spec sequence, actually it will be involved several people like Quillen, Dan Kahn, Curtis, Bausfield, Rector, and several people. They take a serious works to establish the unstable atom spec sequence. What they do, just do a simplicial set. You can apply like a Kamp's construction, like a looping, produce a simplicial group, and then you look at the more lower central series of that, and that's it. So you try to identify E1 term, so-called lambda algebra, E2 term, that will be the EXT groups of the unstable modules over the standard algebra. And the infinity term will be convergence theory. You have to see the homotopy group there. And well, as you see that actually this, you could happen that in one space, same homotopy type, you have a different, totally different simplicial group version in terms of groups. For example, I can get a simplicial group, each level dimension-wise group is given by perfect. In other words, if you apply this lower central series, it may give you nothing. But there may have some different filtrations. That means you get different spec sequence. So this is the theory of the simplicial groups. Okay, so now let me say a little bit more on the homotopy groups, right? So the homotopy group from the definition, it just look at the you use a sphere, like n-dimensional sphere. You look at the pointed maps from the n-dimensional sphere to a space, okay, pointed space, and then you take the homotopy classes of that, right? And it measures complexity of a singular n holes in X, in space X, right? So I should give a remark that nowadays people in science community knows a lot like topological data analysis, and they will say how to describe higher Beatty numbers. Well, they say, okay, it measures complexity of the n holes for space. Strictly speaking, this is not exactly correct. In other words, you get n-dimensional homology may not exactly measure the n-dimensional holes. By means a holes, a singular holes means the mapping flow sphere. So homotopy group is exactly measured. But more or less, this is correct because there's a Horowitz theory and there's mapping flow homotopy group to homology. Now, the homotopy group also plays as a building blocks for cell complex, right? So if you touch growing the cells, each time you have use sphere to map in there, and that's why it began to be important in algebra topology. So if you try to classify the finite complex up to homotopy, you have to deal with the homotopy group. Now, I have to make a remark that even if you know the homotopy group, well, the step to classify the finite complex up to homotopy is also still non-trivial. Okay, so it deals a lot. So in homotopy theory, each step is non-trivial in the sense, assume you know all homotopy group of spheres. If you go to classify the two cell complexes, right? You get sphere growing by another sphere. That actually is also non-trivial. Now, even if you know the homotopy group of sphere, you try to classify, say, three cell complexes, it's still non-trivial. So each step you need significantly different here. Now, well, a lot of works with the homotopy group. I just say a few things like these Tom's work on coordinates. You have to create the use the Tom spaces, create the Tom spectrum, and then you can produce the for coordinates ability to become converged into the problem to determine homotopy group of a Tom spectrum, and Tom successfully solved that and get the fused metal, right? And the Quillen is actually defined the higher algebraic theory using homotopy group. So what do you need to do? You start with a ring, so you look at the general linear groups over that, and then you get the class one space, and then apply the Quillen's plus construction, so you get the space by keeping homology, and higher homotopy groups shows up as the hierarchy theory. And well, the second actually used the great at that time got very nice ideas to be able to show that like high homotopy groups of spheres actually are finite group, except the exceptional case, right? And his ideas basically should be, I think, nowadays called localization theories. Well, now say recently you can see these solutions of the covariant invariance one problem by Mike Hill, Mike Hopkins, and Doc Rabno. It's actually they deal with some, you have to handle some special elements in homotopy groups, or they say the high differentials in atom spec sequence. Okay. Now, so also these structures of finite of the homotopy group of finite complex will be important. The homotopy group, of course, are far unknown, and yeah, it's quite a challenging problem, right? Now here's I show a little bit for the informations the high homotopy groups, right, or S2. So well, this is taken from the table in Toda's book published in 1962. Okay, so you will see the homotopy group of two spheres. So it appears like this. Well, okay. So now I tell a little bit about my work on this direction. Okay, so this work was done in my thesis. So here's how I deal with some give a combinatorial description of general general homotopy group of S2. So you can construct a concrete combinatorial group, right? So say the group GM is n generators, right? You put the letters x1 up to xn, and you put some first relation looks like it's okay. You just make product of this element to be 1. Now, second relation, you deal with all possible a to the commutators, right? If each generator appears to be at least once, all these commutators just make it to be trivial. Okay, so that's the group you can define. Now it turns out the center of this group exactly appears as the nth homotopy group S2. Well, there of course there's some similar description for S2, say wedge S2, and or generally suspension of K by 1. So let me make a remark here. Well, so S2, right? That's like a two-dimensional sphere. It looks like a simple object, right? Now, if you take a two-dimensional sphere, you take one point union. That's called wedge. Actually, the homotopy group of S2 wedge S2 is a monster. It is huge. If you do the given by Hilden-Milner theorem, you will see that it splits up. So all homotopy group of any dimensional sphere and all stable homotopy groups of spheres will become to be summations of the homotopy group S2 wedges 2. Okay. So this is really the big one. Another one for suspension K by 1, right? K by 1 means just classifying space of any group pi. Well, if you do suspension one time, it will be, well, for any path connected space, if you do suspension, well, you can find a certain group of pi whose suspension K by 1 is a weakly homotopy equivalent to space. So this is actually for any suspended space. Actually, you can see homotopy group equivalent. This was done by the common consistent theorem. Okay. Now okay, so now let's say I read some information. This will be a result of earlier. One direction of this is like a so-called the high Van Kempen type theorem for high homotopy groups. We see that for fundamental groups, the Van Kempen ciphered Van Kempen theorem is quite important widely compute that. Now the question, what happens for higher homotopy groups? Well, in 1980s, actually, Brown-Lode has been given like a Van Kempen type theorems for pi 2 and pi 3. And later, actually, it's Alice and Stenner is actually generalized for general pi m. There are some mistakes, and until 2010, it actually finished by Alice and Mikollov. It's give a proper proof of that. And I should mention that this actually the connection between my result and these like Alice Stenner on the or Brown-Lode's one is expected by Bosfield when I was talking to him in 1995. And this work can be generalized later, actually, to look at the homotopy co-limit of cubical diagrams. So let's report for the Van Kempen type theorem. Another thing is that you can look at actually is Mikolov is my course. We have a lot of papers, and he tried to use homotopy group to attack the long-standing problems in the in group theory, so-called the dimension quotients. Okay, well, it means what? Okay, so I just take maybe a shortly description for the problem. So you given any group, you can look at the group ring, okay, over integers, and look at the augmentation ideal filtration. So if you put 1 plus IM, so M for the product of the augmentation ideal, it will give create a subgroup intersecting with group, give a subgroup, so-called dimension subgroup. And I think in 1935, so Magnus shows that if it's a free group, this dimension subgroup will coincide with the nth terms of the lower central series of the group. And there will be a lot of trouble happened in group series. For group series, they believe that for any groups, they should be a coincide, including Magnus. And until 1970s, Rips give a counterexample that the dimension subgroup is actually different from the lower central series. And then people in group theory believe that, well, let's give example, you get Z2. And people believe that the gap may be only given by 2 torsions. And so until recently, Roman Mikhailov actually is exactly use my description to construct the example for groups. Let's say make a torsion of the homotopy group of S2 batch S2 will be embedded into these 2 dimension quotients. That shows that for any order primes, so any power exponents can be in the dimension quotients, right? So that the okay, so now that's like part of the dimension quotient. Now another direction I will try to move to the how we go to braid group, right? So along this direction, you look at the arting representation of braids to the automorphism group or free group. It turns out the group what I constructed for describing homotopy group of 2 sphere, that means simplicial, so it's canonically. That gives a way to show that that this center of this group GM exactly by the fixed point of a pure braid group actions on this group. And if you look at the general group actions or PM actions on this group GM, well, it will give some subgroup of a homotopy group of an element of exact order of 2. Now, this along this direction, actually, I will move further. We found that we should establish more directed connections between the homotopy groups and the braid groups. So let's move to our work on the Brownian. Look at the Brownian braid. So by means of Brownian braids, so you take a braid, if you remove any one of the strings, it becomes trivial, right? So you have the n strings. So take first one, take or second one. Any one of them becomes trivial. So this is so-called Brownian braid. Now you can look at the Brownian braids over 2 sphere, S2. You can look at the Brownian braids over disk. That's the usual, the classical arting braid group. And you can consider the disk as the, say, upper hemisphere, right? So you get a canonical homomorphisms from the braid group over D2, go to braid group over S2. And that will give a group homomorphisms from the Brownian braids over D2 to Brownian braids S2. Well, it turns out that you can see what happens. Well, you can look at the co-kernels. We can see the image of F star is a normal subgroup of the Brownian braids of S2. Turns out co-kernel exactly given by homotopy group S2. Okay, and so you get a sharp exact sequence. Well, this is a work. It seems we got a lot of positive reaction from the community. Like so, also will be highly recognized by society as well. Okay, and so now let me take one conclusion, one immediate conclusion. There's a ceiling actually we got like 10 years ago, right? So any homotopy group S2 is not 0. This so-called, this is called non-triviality. Although you don't know what the pi ms2 is, but we know that for any n greater than 2 is always not 0. And use that, we can see that for Brownian braids of D2 to Brownian braids of S2, it's never onto. Okay, so always some elements. And there's a lot of other, questions. Of course, you can stand it to look at the like a mapping class group and look at the algebras over there, and also you can look at the link groups as well, right? So a lot of also I should mention that this is the technicals we used here is to look at, as I said, use the cross the simplicial structures. And if you pay attention for some recent work on the stability of the cohomology of manifolds, you can apply these skills. But look at the homology, you can get a lot of results as well. Or you can apply other cases. Okay, so now let me say a bit on the for knot theory, right? So for any knot or link, well, you can look at the fringed knot or fringed link. So in other words, you get a knot or link, you just make no over 0 normal vector fields put in there, right? And then you can do the what we call naive cabling. So you just along this direction, cutting the links kind of more and more, and become to be a sequence of the links. Then you just take a link group. In other words, you just look at the complement and then take the fundamental group. That will create exactly simplicial group. Okay. And so in this way, it looks like a construction quite naive. Now the first fundamental question, what's the homotopy type? How you get it? Well, the answer is that you just remove those components of the links which are trivial link, a trivial knot, like in the with trivial fringe. Forget those part, the remaining piece, well, exactly gives the homotopy type of this simplicial group obtained in this way. So in other words, simplicial group will be homotopy equivalent to loop of a wedge of 3 copies of the 3 sphere. Okay, as I mentioned again. So for if you take a 3 sphere in the wedge of 3 sphere, well, the homotopy group is also monster. Okay, it will including the stable homotopy group sphere as a summand as well. Okay, now let's more in this direction. So you can see that if you do look at the slight different view, rather instead of look at the simplicial work resolution work like this, make the simplicial groups, you can look at the cubical diagrams. Through that direction, actually, you can see that the homotopy group can be exactly connected to the link group, like you call like intersections. Well, each AI, you can think about like give a link. You can look at normal closure of the eye's meridian, right? So you can ask what's going on for the intersection subgroups. And then there's another part of the so-called commutative, because the AI, the normal closure means the meridian and the conjugation of that, possible conjugation and generalized subgroup, right? So then you can look at the so-called the commutative subgroup, right? And so you make a symmetric way, and you look at the gap of these, and the gap exactly detected by the homotopy groups. Okay, so that's the result we can get. And okay, so now along these ideas, you can see that you will go beyond a bit simplicial. I just look at the combinatorial way, right? Using these ideas. And one thing is that people working in group theory will be interested for homomorphisms, right? Instead of it looks like if I get group or monoid, I look at the functions between these. Well, if you look group theory, it looks like this is what it means. But if you look at as these functions, okay, so as natural, in other words, that will give a topology. Okay, so that's how topology related to category. So the example you can think about the free monoid construction. So give a set, I can always produce a monoid, free monoid. I can produce free groups. then you can look at all possible natural transformations between them. Well, for this set, you can replace, because it is natural, you can replace set by a simplicial set. In other words, you produce the natural transformations for spaces. So this is how you go to topology. And that will be, say, from this production, you can produce some, actually, Flarecombe produce concrete constructions of some subgroup of natural transformations between like this so-called James construction, okay, free monoid with base point equal to 1, and Milner's construction, free group will make a base point of 1 and work out that. Well, and then from these category views, you can think about, okay, so now I'm doing another way. So let's forget these groups. I go to algebra, right? And the Hopf algebra. Well, typical Hopf algebra is tensor algebra. Forgot multiplications. Only look at the natural transformation as a co-algebras between the tensor algebra itself. And then the question will move to about the factorial version of Bankeley-Birkhoff-Witten theorem. And well, if ground field is 0, it's like in rational case, it works well for Bankeley-Birkhoff-Witten theorem. For factorial version is perfectly. But for general characteristic, you will discover that it is equivalent to look at the modular representation theory of like Lie powers as a modules over symmetric group. Okay, and also is you can see it's actually equivalent to look at the fully Lie algebra terms, the component homogeneous components of Lie powers, or as a modules over general linear groups. Okay, so there's a lot of things now in this package. You will see that a lot of fundamental connections between our stories. Okay, and they will produce a lot of applications in topology. For example, you can produce periodicity of unstable periodicity of homotopy groups, and you can discuss the p-local and the p-modular hyperbolicity of homotopy group, and so on and so on. Okay. Now, okay, so now let me move to the last part. How can we make the applications of topology? Okay, so one thing in our application try to apply topology. So before I arrived, returned to China, I think in the area of the applied topology in China was empty. So we try to produce some new applied topology series to make some application like there's our own style of the applied topology, right? On say topological data analysis and topological AI, so we went to push. And this theory exactly use its Professor Yao's theory on you should produce the topology on digraph. Okay, so digraph is a model, good model for complex networks. So this the theory actually was introduced by Professor Yao in 2012. Okay, so well, originally called path homology, now it's called GLMY homology. And well, if you search history, there's some the motivation of these physicists that has been produced these ideas in 1990s. The physics has been trying to think about how to develop like a discrete differential calculus, right? And one approach tried to use like to make a discrete version of the Helm cohomology. But as usual, physicists may have very smart ideas, but they may not produce like a solid map theory. So in the early work of 1990s, they may give some examples and without theories. Until like in Professor Yao's paper is 88 pages, give full like established full topology theories on the diagrams. And now the basic idea, as I said, that okay, only say basic because time I only explain. So basic idea is for this GLMY homology actually is very deep. So if you look at this, there's many people look at it, how can you do like high categorization on categories? Well, one way is just look at the extent of a nerve complexes. Okay. So that will give, as I said, generalized to infinite category, whatever you want to talk about. But the fundamental piece is the nerve complex. And now you can see now, well, for nerve complex, now you think about what's the difference between category and diagram of quivers. Well, category has a composition operation. Now, diagram and quivers, you can think about the God-given map objects for complex network. You cannot, you may not assume that the existence of composition. So, but you can look at all this is given by what? All possible passings. So this so-called path complex. Now the path complex is now have to go beyond algebraic topology or these categorizations because it may not be a simply complex. So you have to deal a lot of technical difficulties. And resolving these technical difficulties that produce, you can extend the simplicial homology to the homology of a path complex. Let's produce the GLMY homology in this long paper. Okay. Okay, so now you see there were some applications. We did say we tried the material science and the life science, right? So we published a lot of work on this. And more importantly, actually, we can apply to complex disease in medicine, so it's really get a successful application for GLMY homology. And well, okay, so now I say another thing I will say that we should move further for GLMY homology, so we can go to generalized GLMY homology. So you can expand from the directed graph, you can go to hypergraph, you can go to directed hypergraph, or you can go to even call super hypergraph, so you more complicated objects. And these more complicated objects can produce mathematical models for high order interactions in complex systems. So that's, and also roughly say that, briefly say that GLMY theory now can maximize the generalization ability of algebraic topology. So give me like a graph, whatever is directed or undirected or mixed or whatever. You give a collection of subgraphs, we can produce topological features from that. So that's the power of these generalizations. And we did successful applications for describe the, to understand the mechanisms of the high order interactions for complex systems. Okay. Now I would say that, well, there's some more things we are doing. So our theory of applied topology is not just say narrowed down to algebraic topology. We can extend it to use the lower dimension topology. So that's recently we also extended as a part of GLMY theory, we extended to look at the knot theory. And the traditional knot theory will be used in data analysis limited because you are studying look at the quality, classifying the knots. Now we try to make a computation. So as a quantitative tools, let's make it successful to the knot data analysis. As I said, well, I should mention that this is our first time to introduce this new area called knot data analysis, just last October. Okay, so now I would say that, well, the GLMY theory will be underdeveloped. So instead of let's look at the homology theory, we also move to homotopy theory as well. And one important thing is that this homotopy for diagram, if you look at the definition, you can easily see this describe the dynamics of the subgraphs. Okay, so this one step is moving. So from that, you will see that there will be a lot of works has to be done in near future to develop this theory. Okay, so now I will say that I try to give a bit of summary what our research is. So algebraic topology, you can think about there are three views from my point of view, three views to see that. So algebraic topology as a subject by itself, okay? So what's the core problem? Let's classify finite complex up to homotopy. So the homotopy group is the core component there. In that part, so we did a combinatorial decryption for homotopy group. And we did the fundamental work on the functorial decompositions of looped Coich space. As I explained, it's connected to functorial version of Bank-Leibler-Kopf theorem and the modular representation theorem. Now, algebra topology can be viewed in mathematics, so go beyond algebra topology. So a lot of things like fiber bundles, cobordisms, K-series, a lot of, so it's important in geometry. And in this part, and certainly we try to do is to set up some fundamental connections that will be important for interdisciplinary research between different areas, right? For our part, we set up like fundamental relations between algebra topology and the theory of braids and knots, right? We give a homotopy aspect of knot theory and homotopy theory and the modular representation. Now, also, algebraic topology should be viewed from the science, right? Let's now look at the application, say in AI, in data analysis. Well, from that view, actually, we established the area of the applied topology. I think that's in China, okay? And we're developing GLMY theory. Okay, so now I think I should be, because timing, I should stop here. Okay, thank you.